Let's graph the function f of x equals -2 absolute value of x plus 3. Now we've graphed absolute value before. We're expecting this to look like a V, right? Upward or downward? Downward V, because it has a negative in front of the absolute value. So we need to make a table of values. X's and Y's. And we want to start at our vertex. Our vertex is where the absolute value goes to 0. So the vertex is just going to be at 0. Then we want a couple of points to the right and to the left of there. So we'll say +1, +2, -1, -2. And those are going to be the x values that I'm going to substitute in, find the y's that go with them, and use those as the ordered pairs to graph my function.
What did you say the vertex was?
0.
Where what goes to 0?
Where the inside of the absolute value goes to 0, that's where your vertex is. So if I substitute 0 in the place there, I get -2 times absolute value of 0 is 0 plus 3. So I get the ordered pair 0, 3. Then if I substitute 1 in place of x, I get -2 times 1 is -2 plus 3 is 1. If I substitute 2 in, I get -2 times 2 is -4 plus 3 is -1. What happens if I substitute -1 in? Yeah, we get +1 again, because the absolute value turns the -1 to a +1. -2 times +1 is -2, plus 3 is +1. And if you substitute -2, you get -1. So let's take a look at that graph. Over here, make it a little bit bigger so we can see it. I have the point 0, +3, and that's acting as my vertex. I have the point 1, 1, and 2, -1. Then I have the point -1, 1, and -2, -1. So there is my absolute value graph. Just what we were expecting. We've done that for a while, right? Okay, what we haven't done is talked about the domain and range of this graph. Now you can find the domain without even looking at the graph. We know the domain is just anything except the restrictions. Are there any restrictions for this original problem? No, it doesn't have any variables in the denominator, it doesn't have any even radicals. So the domain is all real numbers. You should also be able to look at the graph and tell the domain. See how it's spreading out forever in both directions, this way and this way, indicating that all of the x's will eventually get used. There's nothing keeping them from being used. You all okay with that? Most people do okay with domain. Where people get into trouble is the range. Talk to me about the range of this graph. The range is all of the y values that get used. Does every y value get used?
No, it's every y value under. I mean above. Yeah.
It's every y value under 3, right. So we know that from the bottom here up to 3, everything's good. But after 3, none of these values up here are getting used. So I need an interval that says everything below 3. Negative infinity up to 3. Now we need to know whether to put a bracket or parenthesis on that 3. A bracket because it actually gets used. We can see it. It's actually a y value right here. So that's how you find the domain and range from a graph. Now let's take a look at the function f of x equals the square root of x minus 2. First off, we know that that particular graph has some restrictions. We know that x minus 2 can't be negative, right? Which means that x minus 2 must be greater than or equal to 0. So x has to be greater than or equal to 2. So I'm only going to make a table of values for x values starting at 2 and getting larger. So if I let x be 2, I get the square root of 0 is 0. If I let x be 3, I get the square root of 1 is 1. And if I let x be 4, I get the square root of 2, which I don't really know, but we can see that as a decimal. What is the square root of 2? 1
4.
So about 1.4. Well, square root of 5, if I put 5 in, I get the square root of 3. How about 6? If I put 6 in, what do I get?
2.
Square root of 4, which is 2. So those are some good numbers to kind of use for your graph. We're expecting this to be half of a sideways parabola because we've done these before. So the point 2, 0, then the point 3, 1, and then 4, 1.4, and then finally out here at 6, it hits 2. So we have a little curvy thing right here. There's the graph of f of x equals the square root of x minus 2. Can anyone tell me the domain of that graph? Well, look back at the original problem. What were its restrictions? X had to be greater than or equal to 2. So take a look. Run your arm from the far left to the far right. Am I using any of these x's over here to the left?
So it's greater than or equal to 2.
Mm-hmm. I'm not even using the x's until I get right here to this first x right here. I'm not using any of them until I get to 2. And then I'm using all of the x's thereafter. So all of the ones out here. So we would say that's 2 to infinity. You should be able to do that without a graph. You should be able to find the domain just based on the restrictions as we did at the beginning of this section. The range is the one you're really going to need the graph for. Take a look at the graph over here and tell me about the y values starting at the bottom. Are any of the negative y's getting used?
No.
No. In fact, the first y value that gets used is this one, and that's called 0. And then they get used above that, and it's going to continue to go up from there as the x's get bigger. So we say the range is everything greater than or equal to 0. So the range is bracket 0, comma, infinity. That brings us to the vertical line test. The vertical line test is simply a way of looking at a graph and determining whether that graph is a function or not. Basically, it says that if you have a graph and you imagine running a vertical line through any part of it, it can only hit it once. It can never hit it twice. So here, any vertical line I draw hits that graph how many times? Once. So we say this is a function. We say it passes the vertical line test. However, if I looked at a graph that looks like this, and I imagined drawing a vertical line through there, I could hit that vertical line twice. If it can hit, any vertical line can be hit more than once by the function. By the graph, it is not a function. We say it fails the vertical line test. So this one is not a function. It fails the vertical line test. Does that make sense, guys? Okay, well, really quickly, you look at these three and determine whether they are functions or not functions. So the first one is a circle, and I could draw almost anywhere on it and hit that circle twice, so we say that it is not a function. The next one is actually a cube root function. You probably don't know that yet, but that's what it is. And you imagine any vertical line that I draw through there hits it how many times? Just once. So it is a function. And this one is a sideways parabola. Obviously, it is not a function. And that takes care of the vertical line test for functions. The last thing in this section just hops back, for some reason, to applications of lines. So like I said, there's a lot of weirdness in here. There's domain, there's range, there's basic graphing, there's difference quotient, there's the vertical line test. So it's just kind of a mix-up of a whole bunch of things. And now we're going to jump back. We're going to talk for a minute about linear functions. We just finished a whole unit, basically, a whole chapter on lines. Chapter 2, right? Basically was all about lines. So let's talk a little bit about them. Remember that a linear function is a function that can be determined by an equation of the form f of x equals mx plus b or y equals mx plus b. So basically, all functions, sorry, I said it backwards, all lines are functions except for one type of line. What's the only line that is not a function? Vertical line. A vertical line automatically fails the vertical line test, but every other type of line is a function. Horizontal is a function, positive slope is a function, and negative slope is a function. And as long as it's not a vertical line, it can be written in the form y equals mx plus b. Got it? Okay. So we want to look at this example, and it says that the cost associated with a fraternity dance is $300 for the country club rental and $24 for each couple that attends. All right, let's talk through it one more time. The cost associated with a fraternity dance is $300 to rent the country club, plus $24 for each couple that attends. Got it? Okay. We would like to write the cost equation C of the dance in terms of the number of couples attending. And they say let the number of couples be X. This is meant to be extraordinarily easy for you. So what are we going to let the Y be? Capital C. That's going to be your cost. Okay? So the total cost is going to equal how much per couple? $24. So every couple has to pay $24. So 24 times the number of couples plus, what's that flat fee we have to pay?
When the bell rings.
That flat fee that everybody has to pay. It's a flat fee of,
300.
but it's just paid once. We don't pay that one X times. Did you guys understand that? So it's really easy to write a linear function for a situation. Once we do that, we can find different things based on those variables. So what if I ask you to find the cost if 45 couples attend the dance? That means I should substitute 45 in the place of X, and I'm asking you to find capital C. Capital C equals 24 times 45 couples plus the $300 rental fee. What's that cost? $1,380. $1,380. So that wraps up example 8, and we have one more example to get through, and we will be finished for section 3.1. The target heart rate at which a person should train to get an effective workout is a linear function of his age. So we know it's linear, and it depends on the age. For a 20-year-old starting an exercise program, the target heart rate should be 120 beats per minute. So I know that if you are 20 years old, what should your target heart rate be? 120. I know that for a 40-year-old, the target heart rate should be 108 beats per minute. We just would like to find the linear equation that goes through those two ordered pairs, and that will give us a function of heart rate versus age. So what do we do first? Find the slope, and then once we know the slope, we can plug it into point slope form. Okay, let's get started. The slope is y2 minus y1 over x2 minus x1, which is 12 over 20, and that reduces to what? Negative 3/5. So there's your slope. Then we can plug into the formula y minus y1 equals, in parentheses, x minus x1. So y minus 120 equals m x minus 20. And that gives us y minus 120 equals negative 3/5 x plus 12. And finally, y equals negative 3/5 x plus 132. That gives us the equation, and now all we have to go back through and do is replace the x's and y's with the variables they're asking for. They're telling us to let the age be capital A, and here our age is our x's. So I'm going to replace the x with capital A, and I'm going to replace the y's with capital R for heart rate. And that's all you do to write a linear function.